Pick any astronomy textbook off any shelf in the world, and somewhere in the first few chapters you'll find the same sentence, worded slightly differently each time, but always carrying the same quiet reassurance. The nearest star to our Sun lies 4.24 light-years away. It's presented almost like a piece of good news. Of all the hundreds of billions of stars scattered across our galaxy, here is one close enough to name, close enough to point a telescope at, close enough that the number describing the gap between us fits comfortably in a single sentence. 4.24. It rolls off the tongue. It sits to decimal places deep, suggesting precision, suggesting something measured and tamed and understood. It is the kind of number that invites confidence. Surely, you might think, if the nearest star is only a few light-years away, then visiting it is simply a matter of patience and sufficiently advanced engineering. Surely, it's a problem of degree, not a problem of kind. This video exists to dismantle that comfortable illusion, piece by piece, number by number, until nothing remains of the idea that 4.24 light-years is a small distance. By the end, you will understand exactly why the nearest star in the entire universe, the most favorable, least challenging interstellar target that will ever exist for human civilization, is still, by any honest engineering standard, completely unreachable with anything we currently possess or are currently building. If that thought unsettles your sense of scale, that's the point. Settle in. This is a long one, and it needs to be, because the distance we're about to examine refuses to be summarized in a soundbite. Let's begin. Before we can appreciate how far away Alpha Centauri is, we need to understand what it actually is, because most people who casually reference the nearest star are picturing something simpler than reality. Alpha Centauri is not a single star. It is a gravitationally bound system of 3 stars, located in the southern constellation Centaurus, a constellation that never rises above the horizon for most observers north of the equator's middle latitudes. For anyone living in the southern hemisphere, though, Alpha Centauri is unmistakable, one of the brightest points of light in the entire night sky, outshone by only a small handful of other stars. To the unaided human eye, Alpha Centauri looks like one single, brilliant star. It takes a modest telescope to reveal what's actually there: 2 nearly sun-like stars locked in a long gravitational embrace, orbiting their common center of mass once every roughly 80 years. These are Alpha Centauri A and Alpha Centauri B. Alpha Centauri A is the senior partner. It's a G-type main sequence star, the same broad category as our own Sun, just slightly larger, slightly more massive, and slightly more luminous. If you could somehow stand on solid ground in its habitable zone and look up, the star overhead would look remarkably familiar, a yellow-white disk not unlike the one we grew up under. Alpha Centauri B, its companion, is a notch smaller and cooler, classified as a K-type star. It's dimmer than A, but still a substantial, long-lived stellar furnace in its own right, the kind of star that could plausibly host stable planetary systems for billions of years. The 2 stars swing around each other at distances that vary considerably over their 80-year orbital cycle, sometimes as close together as the distance between our Sun and Saturn, sometimes as far apart as the distance between our Sun and Neptune. This is a true binary system, not a temporary alignment. The 2 stars have been gravitationally bound for billions of years, with an estimated age close to that of our own Sun, somewhere in the range of 4.5 to 5 billion years. Then there's the third member of the family, Proxima Centauri. Proxima is dramatically different from its 2 larger siblings. It's a red dwarf, carrying only about 1/8 of the Sun's mass and a tiny sliver of its luminosity. It is so faint that, Despite technically being the closest individual star to Earth, it cannot be seen without a telescope at all. Proxima orbits the central AB pair from an enormous distance, something in the neighborhood of 13,000 astronomical units. A single astronomical unit being the distance from Earth to the Sun. At that range, Proxima takes somewhere around 500,000 years to complete one full orbit around its two companions. For decades, astronomers weren't even fully certain Proxima was gravitationally attached to the pair at all, rather than simply a chance alignment along our line of sight. It wasn't until 2017 that careful measurements of its motion confirmed the bond. Proxima Centauri is a true member of the Alpha Centauri system, just an extraordinarily distant and dim one. Because of its position in that vast, slow orbit, Proxima currently happens to be the closest of the three stars to Earth, about 4.24 light-years away. Alpha Centauri A and B, slightly farther out, sit at roughly 4.37 light-years. The difference is small on a cosmic scale, but worth noting, and it won't last. Over tens of thousands of years, Proxima's position in its orbit will shift, and eventually one of the larger stars will take over the title of nearest star to the Sun. But for now, today, this moment in cosmic time, Proxima Centauri holds the record. 4.24 light-years. Say it again, it still sounds small. That's the trap we're about to climb out of. Light-years are, in a strange way, a unit designed to make distances sound smaller than they are. The word year is doing a lot of psychological work in that phrase. A year is something we live through constantly. We mark birthdays in years. We measure leases, mortgages, school terms, and careers in years. When a distance is described using a unit built from something so personally familiar, our brains quietly substitute the comfort of year for the genuine scale of what's being measured. So let's strip that comfort away and convert the number into something with no emotional shortcuts attached. Kilometers. Light travels at approximately 299,792 kilometers per second. In a single year, that adds up to roughly 9.46 trillion kilometers. Multiply that figure by 4.24, and the distance to Proxima Centauri comes out to approximately 40.1 trillion kilometers. 40 trillion kilometers. In miles, that's roughly 25 trillion in astronomical units, the standard yardstick, where 1 AU equals the Earth-Sun distance. Proxima Centauri sits at around 268,000 astronomical units away. These numbers are already well beyond what human intuition can process. A trillion of anything defeats casual comprehension. 40 trillion of something as substantial as a kilometer is simply outside the operating range of the human imagination. So instead of trying to picture 40 trillion kilometers directly, let's build the scale up piece by piece, using something we do understand: speed. Light is the fastest thing in the universe. Nothing carrying mass or information can outrun it. And light, the undisputed speed champion of physical law, is still slow enough relative to interstellar distances that its travel times become genuinely meaningful. Light covers the distance from Earth to our moon in about a second and a third. It reaches the Sun in a little over 8 minutes. It races past the orbit of Neptune, the outermost major planet, in roughly 4 hours. Light is fast enough that in a single second it could circle the entire Earth more than 7 times, and light needs for years and roughly 3 months to cross the gap between us and Proxima Centauri. Sit with that for a second. A beam of light leaving Earth tonight, traveling at the literal cosmic speed limit, the fastest anything can possibly move, would not arrive at the nearest star until several years from now. Whatever you're doing in this moment, finishing a degree, raising a child, building a career, That photon is still in transit, still crossing empty space, having covered only a fraction of the distance by the time you've lived through years of your own life. That is the fastest possible crossing. Nothing with mass has ever come remotely close to matching it, and it still takes years. It isn't just that the distance is long, it's that the space filling that distance is almost perfectly empty. The average density of interstellar space in our part of the galaxy is roughly 1 atom per cubic centimeter. For comparison, the best vacuum chambers human engineers have ever built on Earth are still millions of times denser than that. Between here and the Alpha Centauri system, there is essentially nothing. No significant clouds of gas, no detected rogue planets, no asteroids, no comets, no waypoints, no landmarks of any kind. Just a stretch of near-perfect emptiness, 40 trillion kilometers long. Here's a way to feel that scale physically. Shrink the entire solar system down so the sun becomes a basketball sitting at the center line of a football field. At that scale, Earth shrinks to a small grain of sand, roughly 26 meters from the basketball. Jupiter becomes a marble at around 130 meters out. Neptune, the farthest major planet, becomes a small pebble 3/4 of a kilometer away. Voyager 1, the most distant object humanity has ever launched, becomes a barely visible speck, roughly 4.5 kilometers out, after nearly 50 years of continuous flight. On that same scale model, Alpha Centauri becomes another basketball, sitting approximately 7,000 kilometers away. That's roughly the distance separating New York City from Rome. The entire solar system, every world humanity has ever visited or even sent a probe near, fits inside a region just a few kilometers wide around our basketball. The nearest star, on this model, is on another continent entirely, and the 7,000 kilometers between the two basketballs contains nothing, no structure, no rest stop, no intermediate destination. It's the equivalent of crossing an entire ocean and a continent with absolutely nothing beneath you but vacuum. This is what the phrase 4.24 light-years hides behind its tidy decimal point. It sounds like a number you could work with. It's actually a void. Let's bring this down to something concrete. Our most distant spacecraft, Voyager 1, launched in September of 1977. Voyager 1 spent its early years studying Jupiter and Saturn before using gravity assists from both planets to boost itself onto an outward trajectory, eventually settling into a cruise velocity of about 17 kilometers per second relative to the Sun, roughly 61,000 kilometers per hour. As of recent tracking data, Voyager 1 sits at well over 170 astronomical units from the Sun, making it comfortably the most distant human-made object in existence. 17 kilometers per second is an extraordinary speed by terrestrial standards. It's more than 15 times faster than a typical rifle bullet. If you could sustain that speed along Earth's surface, you'd circle the entire planet in under 40 minutes. Now point that same speed at Proxima Centauri, at 17 kilometers per second. The journey would take roughly 74,000 years. 74,000 years is not a travel time in any meaningful human sense. It's a geological epoch. 74,000 years ago, anatomically modern humans had only recently begun spreading beyond Africa in significant numbers. Agriculture didn't exist yet. Writing didn't exist yet. The entirety of recorded human civilization, every empire, every written language, every city ever built, fits inside a window of roughly 5,000 to 6,000 years. Voyager 1, at its current speed, would need more than 12 times that entire span just to arrive. And notably, Voyager 1 isn't even headed toward Alpha Centauri. Its actual trajectory carries it toward the constellation Ophiuchus, and the nearest star it will eventually pass, in roughly 40,000 years, at a distance of about a light-year and a half, is an obscure red dwarf called Gliese 445. Voyager wasn't designed for interstellar travel. It was designed to study giant planets. Its speed simply gives us a useful, sobering benchmark. Maybe a more modern probe fares better. Let's check. New Horizons, the spacecraft that gave us our first close-up images of Pluto, cruises at roughly 14.5 kilometers per second relative to the Sun, actually slower than Voyager 1, despite being a more modern design, because it received less favorable gravitational assists along its route. At that pace, the trip to Proxima Centauri stretches to roughly 87,000 years. Worse, not better. What about the Parker Solar Probe, frequently cited as the fastest spacecraft ever built? Here we need to be careful with the numbers. Parker's astonishing velocity, in excess of 190 kilometers per second, occurs only during its closest approaches to the Sun, when it's deep inside the Sun's gravity well, essentially borrowing speed from gravity the way a marble picks up speed rolling downhill. As it swings back outward in its orbit, it slows dramatically, trading that kinetic energy back for height, the same way a ball thrown upward decelerates as it climbs. Parker cannot maintain 190 kilometers per second on an outbound, straight-line trajectory. That speed is temporary and tied to its position relative to the Sun. But suppose, hypothetically, we could somehow extract that peak velocity and sustain it indefinitely on a straight shot toward Proxima Centauri. Even then, the crossing would take roughly 6,700 years, longer than the entirety of recorded human history. Try 100 kilometers per second, a speed no outbound spacecraft has ever achieved, and you're still looking at around 12,700 years. At 500 kilometers per second, a velocity that exists nowhere in current engineering, the trip still takes roughly 2,500 years. Even at a full 1,000 kilometers per second, a velocity beyond anything any propulsion system currently in development could produce for a spacecraft of meaningful size. The crossing still requires more than 1,200 years. Every speed we try, every optimistic assumption we layer on, the answer keeps landing in centuries or millennia. The distance simply does not negotiate. Even setting aside speed for a moment, there's a deeper problem. Nothing humans have ever built is designed to function for tens of thousands of years. Every spacecraft has a finite working lifespan. Metals fatigue, seals lose integrity, lubricants slowly evaporate even in the near vacuum of space. Radiation steadily damages onboard electronics, flipping bits in memory, degrading solar panels, weakening structural bonds over time. Voyager 1 and Voyager 2, the most durable spacecraft humanity has ever built, are already showing their age after less than 50 years. Their nuclear power sources are running low. Mission controllers have had to shut down instrument after instrument simply to conserve the dwindling supply of electricity. The data systems still aboard run on technology designed in the 1970s. Now imagine asking any spacecraft, however well built, to remain functional for 74,000 years. This isn't a difficult engineering problem. It's a problem with no engineering solution at all, given anything resembling current materials science. No alloy, no polymer, no electronic component manufactured by human industry can maintain structural and functional integrity across that timescale without active maintenance. Maintenance that, by definition, can't happen on an unmanned interstellar voyage. Power generation runs into the same wall. Radioisotope, thermoelectric generators, the gold standard for deep space power sources, have fuel sources with half-lives measured in decades, not millennia. Solar panels become essentially useless once a craft is far enough from any star, including, eventually, its own departure star. Nuclear fission systems require fuel that decays and control machinery that itself degrades. No power technology we currently possess can reliably function for more than a few centuries, let alone tens of thousands of years. Then there's communication. Voyager 1, even at its current relatively modest distance, transmits data back to Earth using a low-power radio transmitter and a fumetter dish antenna. At a data rate so slow it would have seemed primitive in the dial-up era. Even now, the signal arriving at Earth is so faint that it takes the enormous 70-meter dishes of NASA's Deep Space Network just to detect it reliably. Signal strength falls off with the square of distance. Double the distance, and the signal becomes 4 times fainter. At Alpha Centauri's distance, roughly 268,000 astronomical units, the signal from a transmitter identical to Voyager's would be millions of times fainter than what we currently detect from Voyager. No existing radio telescope, no foreseeable upgrade to existing infrastructure could pick that signal out of the noise. You could compensate with a vastly more powerful transmitter or a vastly larger antenna, but both options add mass, and mass is the enemy of velocity. Every additional kilogram dedicated to communications hardware is a kilogram that must be accelerated to interstellar speed, which demands more propellant, which adds more mass, which demands still more propellant. It's a spiral with no natural exit. And even setting the engineering aside, there's a more unsettling question. Who, exactly, is listening after 74,000 years? What institution maintains a receiving station across that span? What government, what culture, what language even survives intact? The oldest continuously functioning human institutions, certain religious orders, certain universities, stretch back roughly 1,000 years. No human organization of any kind has ever persisted for 74,000 years, not remotely close. Launching a probe on a journey that long isn't a mission plan. It's an act of faith in the permanence of civilization, a faith with no historical precedent to support it. The obvious counter-argument arrives quickly. If no single human can live long enough to make the crossing, why not send a self-sustaining population instead? A ship large enough to support generations being born, living, and dying aboard, while the vessel slowly crosses the gap. Science fiction has a name for this: the generation ship. It's an elegant idea on paper. It collapses almost immediately under real scrutiny. Start with genetics. A population sealed inside a vessel for tens of thousands of years needs enough genetic diversity to avoid the slow accumulation of harmful traits that comes from a small, closed gene pool reproducing within itself across countless generations. Estimates for the minimum viable population on a journey of that length tend to land somewhere in the hundreds to low thousands. Assuming strict and continuously enforced reproductive management across every single generation for the entire duration of the voyage. Several hundred to several thousand people isn't a crew. It's a small town, one that needs food production, water recycling, waste processing, medical care, education systems, conflict resolution, and governance, all functioning indefinitely with zero resupply from Earth, zero replacement parts, zero emergency imports of seed stock or medicine or rare materials. The ship has to carry or manufacture everything its population will ever need across a span roughly 15 times longer than the entirety of recorded human history. No closed ecological system humans have ever built has come close to that level of self-sufficiency. Biosphere 2, the most ambitious sealed habitat experiment ever attempted on Earth, suffered serious oxygen depletion and crop failures within its first 2 years. Despite being built on the surface of a planet with abundant sunlight, stable gravity, and the option of emergency intervention if things went badly wrong, the International Space Station, humanity's most sophisticated space habitat by far, depends on constant resupply missions from Earth. A generation ship would need to replicate the ecological stability of an entire living planet using only what it carried at launch, with zero room for systemic failure across thousands of years. And the sociological problems may be even harder to solve than the engineering ones. A generation ship isn't just a machine, it's a civilization in miniature. And civilizations don't hold still. Languages drift, cultures shift, belief systems rise, fracture, and disappear. Political structures transform, sometimes violently, sometimes within a single lifetime. The descendants who arrive at the destination, dozens of generations removed from the founders, would likely share almost nothing culturally with the people who first boarded. They might not speak a mutually intelligible language. They might not share the founders' reasons for the voyage at all. There's also an uncomfortable ethical wrinkle that generation ship proposals tend to skip past. The first generation chooses to board. Every subsequent generation does not. They're born into a sealed vessel they can never leave, committed from birth to a mission they had no say in, traveling toward a destination that won't arrive in their lifetime, their children's lifetime, or their grandchildren's lifetime. For dozens, maybe hundreds, of generations, every single person aboard lives and dies in transit, never seeing the world their ancestors left, never seeing the one their descendants might reach. Over a span of 74,000 years, every conceivable form of social breakdown, civil conflict, famine from ecosystem collapse, technological regression, disease sweeping through a population with no outside medical support, isn't just possible. It's close to statistically inevitable. The ship wouldn't need to survive one crisis. It would need to survive every plausible crisis in sequence, for longer than any human civilization has ever existed on solid ground. A generation ship doesn't solve the distance problem. It just restates it in biological and sociological terms instead of mechanical ones. And based on everything we know about closed ecosystems, population genetics, and the historical track record of human institutions, the honest answer is that it probably can't be solved that way either. Not because the idea is physically forbidden, but because the timescale involved dwarfs every known limit of human social and biological endurance. There's another quiet problem buried inside any multi-millennia voyage: navigation. Across a journey lasting tens of thousands of years, even an extremely small initial pointing error compounds into a catastrophic miss by the time of arrival. A targeting error of a tiny fraction of a degree at departure could translate into a final miss distance of hundreds of millions of kilometers, multiple times the distance between Earth and the Sun. Correcting course requires functioning thrusters, functioning sensors, and a functioning onboard computer, all of which need to keep working not for years, but for tens of thousands of years. No thruster system retains usable propellant that long. No sensor stays calibrated across that span. No computer runs flawlessly for centuries, let alone millennia, without failure. And interstellar space, despite its overwhelming emptiness, isn't a perfect vacuum. It contains scattered dust grains, some no larger than a few microns across, drifting at relative velocities determined by the spacecraft's own speed. At interstellar cruising speeds, even a microscopic dust grain carries enough kinetic energy on impact to threaten sensitive components. Across a journey lasting tens of thousands of years, the cumulative odds of a damaging impact stop being negligible. No shielding technology we currently have can guarantee protection against every possible micro-impact over a timescale that long. The medium is sparse, but time, in this case, is overwhelmingly abundant, and probability eventually catches up. At this point, it's natural to ask, fine, current speeds are hopeless, but what about propulsion concepts that don't yet exist at scale, but aren't forbidden by physics either? Ion propulsion is one of the more mature options. Instead of a brief, violent chemical burn, ion engines accelerate charged particles using electric fields, producing a gentle but continuous thrust sustained over long periods. NASA's Dawn mission, which explored the asteroid Vesta and the dwarf planet Ceres, demonstrated impressive cumulative velocity changes using exactly this approach. But even the most advanced ion propulsion concepts top out in the range of tens of kilometers per second of exhaust velocity, nowhere near what's needed for interstellar travel, even after years of continuous thrusting. A more advanced variant, sometimes called variable specific impulse magnetoplasma propulsion, promises higher performance, but even optimistic projections keep final spacecraft velocities well under 100 kilometers per second. At that speed, the journey to Proxima Centauri still takes over 12,000 years, excellent for navigating the solar system, inadequate for crossing interstellar space. Nuclear thermal propulsion, where a reactor heats propellant to extreme temperatures before expelling it, offers more thrust than ion engines, and was successfully demonstrated in test programs going back to the 1960s. Modern variants are being studied for potential crewed Mars missions, but its exhaust velocity tops out around 9 kilometers per second, actually slower than Voyager 1's current cruise speed. Useful for shortening trips within the solar system, useless for the interstellar problem. Nuclear pulse propulsion, the concept behind a famous late 1950s study that imagined detonating small nuclear charges behind a spacecraft and riding the resulting shock waves, theoretically could reach speeds in the range of 3 to 5% of light speed, which would bring Proxima Centauri within reach in something like 85 to 140 years. That's a dramatic improvement, but the concept was never built. International treaties banning nuclear detonations in space, combined with the sheer engineering challenge of building a structure that could survive repeated nuclear blasts directly behind it, left this idea permanently on paper. No hardware has ever been built. No test has ever flown. No government is currently funding a vehicle of this kind. Fusion-based propulsion concepts go further still. A famous 1970s study by a British engineering society envisioned an uncrewed probe powered by igniting small pellets of fusion fuel inside a reaction chamber, achieving exhaust velocities high enough to push a payload of several 100,000 kilograms to roughly 12% of light speed. At that velocity, the crossing to Proxima Centauri would take around 36 years, finally within range of a human career, if not quite a casual mission timeline. But this design exists only as a paper study. The required fusion ignition rate, hundreds of precise detonations per second, has never been demonstrated in any laboratory. The proposed fuel, a rare isotope of helium, exists on Earth only in vanishingly small quantities. The most plausible source is lunar soil, where it occurs in concentrations measured in parts per billion, meaning a single mission's fuel supply would require mining and processing millions of tons of lunar regolith. The spacecraft itself, fully fueled, would be a colossus weighing tens of thousands of metric tons, larger than an aircraft carrier. That study was never meant as a construction blueprint. It was meant to prove that interstellar travel wasn't forbidden by physics. It succeeded at that. It did nothing to solve the actual engineering problem. The pattern across every one of these technologies is consistent. Anything that's actually been built and flown produces interstellar travel times measured in tens of thousands of years or worse. Anything that could theoretically shrink the journey to decades or centuries has never made it past the conceptual or paper study stage. This isn't a funding shortfall or a failure of political will. It's a problem rooted in fundamental physics and materials science. Let's put real numbers on why this is so hard. Kinetic energy scales with the square of velocity. Double your speed, and you need 4 times the energy. Triple it, and you need 9 times the energy. This relationship turns brutal at interstellar velocities, accelerating a single kilogram of payload to just 1% of the speed of light. About 3,000 kilometers per second requires somewhere in the neighborhood of 4.5 trillion joules. That's roughly equivalent to the energy released by a 1 kiloton explosive just to move 1 kilogram. Scale that up to a modest 1,000-kilogram spacecraft, and you're looking at energy on the order of a 1 megaton thermonuclear detonation. Scale further to a 100,000-kilogram vehicle, the rough minimum for anything crewed, and the energy requirement climbs into the hundreds of quadrillions of joules just to reach 1% of light speed. And 1% of light speed still means a 400-plus year crossing. Push to 10% of light speed, and the energy cost per kilogram jumps by a factor of 100. A modest probe at that speed demands energy comparable to the total annual electricity output of a mid-sized industrial nation. A crewed vehicle at the same speed would require energy reserves approaching a meaningful fraction of an entire major country's total annual energy consumption for a single mission, with no guarantee of being able to slow down at the other end. These aren't speculative figures pulled from exotic physics. They follow directly from the most elementary equation in classical mechanics. Kinetic energy equals 1/2 mass times velocity squared. There's no clever engineering trick that gets around it. The energy cost of interstellar speed isn't a mystery waiting to be solved. It's a mathematical certainty, and it's enormous. Here's the realization worth sitting with. Alpha Centauri is the nearest star system. It represents the shortest possible interstellar crossing that will ever exist for human civilization. And even this minimal, most favorable case distance defeats every propulsion technology currently in existence. Not because engineers lack imagination, not because scientists lack ambition, but because the distance is so vast, and the energy demands of crossing its scale so punishingly, that the entire undertaking sits beyond what any civilization on Earth has ever built or is currently building. When people hear only 4.2 for light years, they're unconsciously comparing that figure to the unconsciously vast scale of the galaxy, 100,000 light years across, and feeling reassured by the contrast. Relatively speaking, it does sound close. But relatively speaking is the language of astronomers describing stellar geography, not the language of engineers trying to actually build something that crosses the gap. An astronomer can correctly say Alpha Centauri is close in the context of galactic scale. An engineer who actually tries to design a mission runs headfirst into a wall that makes the word close meaningless. Suppose, for the sake of argument, that propulsion technology takes a genuine leap forward, not a marginal improvement, but a true breakthrough. Suppose a future spacecraft achieves a cruising speed of 1% of light speed, roughly 3,000 kilometers per second, about 170 times faster than Voyager 1. Nothing in the history of human engineering has come within a factor of 100 of that velocity. At that speed, The trip to Proxima Centauri takes roughly 424 years, a dramatic improvement over 74,000, but still firmly beyond any single human lifetime, beyond the lifespan of most institutions, beyond the continuous existence of most nation-states in recorded history. Pushed to 2% of light speed, and the crossing drops to roughly 212 years, still longer than any human life, still longer than most governments have ever lasted uninterrupted. At 5% of light speed, the trip shrinks to around 85 years, finally within reach of an extraordinarily long human lifespan, assuming every life support system aboard functions flawlessly for nearly 9 decades straight. At 10% of light speed, the crossing takes roughly 43 years. Now we're talking about a mission duration comparable to a single scientist's career. Someone who helps design the mission in their 30s might live to see results return in their 70s. At 20% of light speed, the target, a real, funded, research initiative, actually aimed for, the trip drops to roughly 21 years. Add a little over 4 years for the return signal to make it back to Earth, and the total span from launch to first data in hand comes to roughly 25 years, a generation, a career, a mortgage. Finally, a timescale that feels almost survivable on a human institutional level. And this is exactly where the next layer of problems reveals itself. Announced in 2016 with $100 million in initial research funding and the public backing of some of the most prominent physicists of the era, an initiative called Breakthrough Starshot set out to prove that 20% of light speed wasn't just theoretically possible, but achievable with technology that already existed in primitive form. The concept was elegant in its simplicity. Build a massive, phased array of ground-based lasers capable of a combined output in the range of 100 gigawatts. Launch a mothership carrying thousands of gram-scale probes, each attached to a thin, reflective light sail roughly a meter across, into high Earth orbit. Fired the laser array at each sail for around 10 minutes, using pure radiation pressure to push the tiny craft up to 20% of light speed. The probes would then coast silently for roughly 20 years, perform a brief flyby of the Alpha Centauri system, capture whatever images and data they could in the fleeting encounter window, and transmit everything home using their own sails as makeshift antennas. Nothing about the concept violated known physics. It relied on technologies that already existed in early, primitive forms: laser arrays, light sails, miniaturized electronics, extrapolated to scales that were ambitious but not theoretically forbidden. Proponents described it as engineering, not science fiction. The physics checked out. The open question was always whether the engineering could be made to work within any reasonable budget or timeline. By 2025, however, independent reporting suggested the project had quietly stalled. Only a small fraction of the original funding had actually been spent across a few dozen research contracts. No full-scale laser prototype had been built. No light sail had been tested under conditions anywhere near interstellar relevant scale. No actual nanocraft had launched on any kind of interstellar trajectory. The project hadn't been formally cancelled. It had simply stopped visibly advancing without the fanfare that accompanied its launch. This isn't a judgment on the brilliant scientists involved, many of whom continue doing valuable theoretical work. It's a judgment on the sheer scale of the challenge. Even the most stripped-down, favorable version of interstellar propulsion imaginable. No onboard fuel, payloads measured in grams, no deceleration, no return trip, just a one-way laser-driven sprint, still requires a ground-based laser installation producing roughly 100 billion watts of focused steerable power. For comparison, Total electrical generating capacity across an entire major industrialized nation is measured in the trillions of watts. An array like this would need to produce a meaningful single-digit percentage of an entire superpower's total electrical output, and focus all of it into a tight beam for a 10-minute burn per launch. And the laser array is only the first hurdle. The sail itself has to survive acceleration forces tens of thousands of times stronger than Earth's gravity. It has to be reflective enough to absorb momentum from the laser without simply melting under the energy load. It has to hold its shape and orientation with precision measured in microns throughout the entire acceleration burn. The onboard payload cameras, power systems, navigation, communications, tiny photon thrusters, all has to fit within a total mass budget of roughly a single gram. The return communication link has to function across more than 4 light-years, using an antenna no larger than the sail itself, transmitting to ground-based receivers sensitive enough to pick up a signal that doesn't yet exist anywhere on Earth. Each of these challenges is formidable on its own. Together, they represent a development program that would likely take decades and cost tens of billions of dollars, orders of magnitude more than the $100 million originally committed, which was always meant as research funding to study feasibility, not construction funding to actually build the thing. And even in the best-case scenario where everything worked perfectly, the resulting mission would be almost absurdly limited. A gram-scale probe traveling at 20% of light speed has no way to slow down. There's no onboard fuel for deceleration, and there's no laser stationed at Alpha Centauri to push back against the craft's momentum on arrival. The probe would simply scream through the entire system at roughly 60,000 kilometers per second, with the entire useful observation window lasting perhaps a few hours at most. Whatever images or data it manages to capture in that brief window have to be transmitted home across more than 4 light-years using a power budget measured in milliwatts. The science returned from such a mission would still be historic. Any image of a planet inside the Alpha Centauri system, taken from up close, would be a landmark achievement in human history. But the mission profile resembles a bullet passing through a room and snapping one photograph in transit, rather than anything resembling sustained exploration. No lingering, no follow-up, no close inspection, no sample collection, no adjusting course based on what the probe actually finds. One brief, irreversible encounter, 40 trillion kilometers from home. Let's return to the energy math, because it becomes more punishing, not less, as speed increases. We already established that accelerating a single kilogram to 1% of light speed costs roughly 4.5 trillion joules. At 5% of light speed, the kinetic energy for a modest 1,000-kilogram spacecraft climbs to roughly 100 trillion joules, comparable to the yield of the most powerful nuclear weapons ever detonated, just to move something about the mass of a compact car. At 10% of light speed, the same spacecraft requires energy in the range of 450 trillion joules, exceeding even the largest thermonuclear test yields in history. At 20% of light speed, the Breakthrough Starshot target, the energy required per kilogram of payload climbs to roughly 1.8 quadrillion joules. For a gram-scale nanocraft, this remains manageable. The total kinetic energy imparted during the 10-minute laser push works out to something on the order of a couple of terajoules. Intense but not civilization-breaking, provided you already have that 100-gigawatt laser array sitting there ready to fire. But scale the payload up. Instead of a gram-scale chip, imagine a real instrument package weighing tens of kilograms, or a probe weighing hundreds of kilograms, capable of actually decelerating and entering orbit, or a crewed vehicle weighing tens of thousands of kilograms, capable of sustaining human life across the journey, the energy requirements explode exponentially. A 100-kilogram probe at 20% of light speed needs energy comparable to the annual electricity output of a mid-sized European nation. A 10,000-kilogram probe, roughly the scale of a large robotic planetary spacecraft, needs energy exceeding the total annual energy consumption of many entire countries. A 100,000-kilogram crewed vehicle at the same speed demands energy on the order of the entire world's annual energy consumption, concentrated into a single propulsion event. And these figures all assume perfect efficiency, every joule converted directly into spacecraft kinetic energy, with zero losses. Real propulsion systems waste enormous amounts of energy as heat, exhaust, and structural stress. Realistic efficiency factors could easily multiply the true energy requirement by a factor of 5 to 10. The energy barrier doesn't soften as speed increases. It hardens. Every additional percentage point of light speed costs dramatically more than the last. Because the underlying relationship isn't linear, it's closer to a parabola, climbing ever more steeply. At velocities approaching a meaningful fraction of light speed, relativistic effects compound the problem further still, as the effective inertia of the spacecraft increases according to relativity, demanding even more energy for each further increment of speed. This is why propulsion isn't simply an engineering problem waiting for a clever fix. It's a problem woven into the basic structure of physics. You can improve efficiency, you can reduce spacecraft mass, you can refine the propulsion mechanism, but the underlying kinetic energy equation remains fixed, and it sets a hard floor on the energy required, a floor that no amount of cleverness can lower. Every figure discussed so far assumes a one-way acceleration, reach cruising speed, then coast the rest of the way. That's the architecture Breakthrough Starshot adopted: accelerate once, never slow down. But a flyby isn't a complete scientific mission in any meaningful sense. If you actually want to enter orbit around a star or planet, land an instrument on a surface, or study a system for months or years rather than hours, you have to decelerate. And deceleration, under the unforgiving math of rocketry, doesn't just modestly add to the energy budget. It can multiply it many times over. This comes down to the foundational equation of rocketry, the relationship between a rocket's achievable velocity, the exhaust velocity of its propellant, and the ratio between its fully fueled mass and its empty mass. After all, propellant is burned. The math is logarithmic. Every additional increment of velocity demands a disproportionately larger amount of fuel relative to payload. Now consider what deceleration means under that framework. A spacecraft that accelerates to 10% of light speed and then needs to stop at its destination has to carry enough fuel not just to reach cruising speed, but to cancel that velocity entirely upon arrival. That deceleration fuel has to be carried during the acceleration phase, which means it too has to be accelerated to cruising speed, which demands yet more fuel to accelerate that fuel, which demands still more fuel beyond that. The compounding effect is exponential, not additive. For a spacecraft relying on onboard reaction propulsion at 10% of light speed, the resulting fuel-to-payload mass ratio can reach into the thousands, depending on the specific exhaust velocity of the propulsion system used. In other words, a spacecraft designed to both accelerate and decelerate at interstellar speeds isn't a vehicle that carries some extra fuel for the return leg. It's a vehicle that is almost entirely fuel, with the actual scientific payload representing a tiny fraction of total launch mass. This is exactly why Breakthrough Starshot chose a flyby-only architecture in the first place. Decelerating a gram-scale probe from 20% of light speed using any known onboard propulsion method would require a fuel mass vastly exceeding the probe's own mass, completely negating the advantage of building something lightweight to begin with. And even setting fuel aside, the laser sail method offers no built-in mechanism for slowing down at the destination at all. The laser stays on Earth, and there's nothing waiting at Alpha Centauri to push back from the other direction. Some proposals explore using the destination star's own light pressure for braking, or magnetic fields interacting with the interstellar medium to slow a craft down. These remain theoretically interesting but largely unproven, and face severe practical limits. Stellar light pressure alone is far too weak to meaningfully decelerate a probe arriving at relativistic speed, and magnetic braking concepts would require enormous superconducting structures and would only work effectively at much lower velocities than 20% of light speed. The bottom line: every energy estimate we've discussed applies only to the simplest possible mission, a one-way non-stop flyby with no ability to slow down, orbit, or return. Any mission aspiring to actually explore the Alpha Centauri system rather than glimpse it for a few hours has to solve the deceleration problem, and solving it at interstellar velocities multiplies an already staggering energy requirement several times over. Let's add one more dimension that often gets quietly skipped in optimistic discussions of interstellar travel: the delay in communication. The speed of light isn't just a barrier to physical travel, it's a barrier to information. Any radio signal or laser pulse sent between Earth and Alpha Centauri travels at exactly the speed of light. No faster, no exceptions. One-way communication takes 4.24 years. A full round-trip question-and-answer exchange takes 8.48 years. This means any probe arriving at Alpha Centauri operates in total communication isolation for the entire duration of its encounter. Mission controllers on Earth can't steer it in real time. They can't adjust its instrument pointing based on what it's currently seeing. They can't redirect it to investigate something unexpected, or warn it away from a hazard it hasn't yet detected. Every action the probe takes during its brief encounter must already be pre-programmed before launch, or decided entirely autonomously by onboard software, with zero input from Earth. For a quick flyby with a simple mission profile, point a camera, take a picture, transmit the data, this limitation is manageable. But for anything more ambitious, the delay becomes genuinely crippling. Imagine a future probe designed to enter orbit around a planet in the system's habitable zone. Orbital insertion demands precise timing and real-time adjustments based on conditions that simply can't be predicted in advance from Earth. If the probe runs into an unexpected debris field, an unanticipated radiation environment, or a navigational hazard, it has to diagnose and respond entirely on its own. Whatever question it manages to send back to Earth won't get an answer for more than 8 years. Now scale this up to an actual crewed mission. Picture human beings arriving at Alpha Centauri after a multi-decade journey, beginning their observations and running into something unexpected: a medical emergency, a mechanical failure, a navigational hazard. They send a message describing the problem and requesting guidance. That message arrives on Earth more than 4 years later. Engineers spend time studying it, formulating a response, and transmitting instructions back. Instructions that take another 4+ years to arrive at Alpha Centauri. More than 8.5 years will have passed since the original problem was first reported. Whatever the emergency was, it resolved itself, one way or another, long before any guidance could possibly arrive. The crew lived or died, succeeded or failed, entirely on their own resources, with Earth functioning as little more than a distant, irrelevant memory during the crisis. This is a kind of operational isolation that no human expedition in history has ever faced. Astronauts on the Moon dealt with communication delays measured in seconds. A crew on Mars would face delays measured in minutes. Challenging, but survivable with good autonomous systems and solid contingency planning. A crew at Alpha Centauri faces delays measured in years. That's not a communication inconvenience. That's functional abandonment. The psychological dimension of this is rarely discussed in depth, but is potentially severe. Humans evolved as deeply social creatures, embedded in communities and constant contact. Even astronauts on low-Earth orbit space stations, just a few hundred kilometers up, report measurable feelings of isolation and psychological strain during missions lasting only a handful of months. Submarine crews on extended patrols show measurable psychological effects. Researchers isolated through long polar winters show elevated rates of depression and cognitive strain. Now imagine a crew that knows with mathematical certainty that no rescue can arrive for decades, that no message from home will reach them in under 4 years, and that every decision, every crisis, every triumph and failure of the mission depends entirely on the people physically present aboard the ship. This isn't exploration in any historically familiar sense. Age of Sail explorers could still make port calls, trade for supplies, interact with local populations along the way. Polar explorers, even when far from rescue, generally knew help was at most months away. A crew bound for Alpha Centauri has no ports of call, no supply convoys, no rescue missions of any kind. Nobody is coming. The stars are simply too far apart for that to be physically possible. And this isolation isn't limited to crewed missions. Even an uncrewed probe at Alpha Centauri is operationally alone, in a way no previous space mission has experienced. Mars rovers regularly receive updated software, revised mission plans, and troubleshooting guidance from Earth, with delays measured in minutes. A probe at Alpha Centauri would need to be programmed with enough built-in intelligence and contingency planning to handle essentially any situation, entirely on its own. Effectively a fully independent scientific agent, capable of deciding what to observe, how to respond to anomalies, and how to allocate its limited resources, all without any meaningful guidance from Earth. The kind of artificial intelligence required for that level of genuine autonomous judgment doesn't currently exist, and even once it does, there's no way to test it against the actual conditions at Alpha Centauri before the probe physically arrives there. There's one more communication-related obstacle worth examining closely: bandwidth. How much data a probe can send back to Earth depends on its transmitter power. Its antenna size, the sensitivity of receivers on Earth, and the distance the signal has to travel. Over interstellar distances, achievable data rates collapse to almost comically low levels. A Breakthrough Starshot style nanocraft, transmitting with a power budget measured in milliwatts across more than 4 light-years, might manage only a handful of bits per second under the most optimistic assumptions. Sending a single high-resolution photograph at that rate could take weeks or months. Even a much larger probe with a dedicated high-power transmitter and a sizable antenna would still face severe bandwidth limitations at this range. Achievable data rates across interstellar distances, even with reasonably foreseeable technology, are likely to remain measured in bits per second rather than the megabits or gigabits we take for granted on Earth. A mission that spends years actively observing the Alpha Centauri system could easily accumulate terabytes of valuable scientific data and then require decades just to transmit all of it back home. The scientific return of an interstellar mission isn't limited only by what the probe can physically observe. It's also throttled by how much of that observation can actually make it back across the void in any reasonable amount of time. Step back and notice the shape of what we've described. This isn't one isolated problem. It's a cascade of interlocking problems, each one feeding directly into the next. The distance demands extreme speed. Extreme speed demands extreme energy. Extreme energy demands either tiny, scientifically limited payloads or civilization-scale infrastructure investment that no nation on Earth has ever attempted. Tiny payloads limit scientific return to brief flybys. Larger payloads multiply the required energy beyond anything currently achievable. Any speed short of light itself imposes years of unavoidable communication delay. Communication delay eliminates real-time mission control. The absence of real-time control demands fully autonomous decision-making. Fully autonomous decision-making demands artificial intelligence sophisticated enough to handle genuine unknowns, which doesn't yet exist in a flight-ready form. And even the data successfully gathered by such a probe can only trickle back to Earth at rates that would feel sluggish by 1990s dial-up standards. Every single one of these problems already exists at Alpha Centauri, the nearest star. The easiest possible target, 4.24 light-years away, not at some far-flung destination 50 or 100 light-years out. Right here, at the closest possible interstellar address, and we haven't solved a single one of them. It's tempting, at this point, to retreat into a familiar kind of techno-optimism. Technology advances exponentially. Today's impossible becomes tomorrow's routine, and we shouldn't assume our current limitations are permanent. There's real truth buried in that instinct. Technology genuinely does advance. Problems that once seemed hopelessly intractable have repeatedly yielded to persistence and ingenuity. But the interstellar distance problem isn't analogous to most of the breakthroughs that optimism narrative usually points to. Early aviation pioneers needed to generate enough lift to overcome gravity at relatively modest speeds. The underlying physics was already well understood, and the remaining engineering gap, while real, was narrow. Interstellar travel requires generating enough energy to cross a gulf so vast that light itself needs years to traverse it. The engineering gap here isn't narrow. It spans many orders of magnitude. The most optimistic propulsion concepts ever seriously studied still require energy outputs exceeding the total current energy production of human civilization as a whole. The physics here isn't quietly waiting for a clever trick to unlock it. The physics is the obstacle. And Alpha Centauri, for its part, is utterly indifferent to our optimism or our timelines. It sits in the southern sky, brilliant and serene, exactly 4.24 light-years away, neither meaningfully approaching nor receding on any timescale that matters to us. It will still be there if we eventually solve these problems. It will still be there if we never do. The distance simply is what it is. 40 trillion kilometers of emptiness, waiting for a species that has, to this point, crossed only a vanishingly small fraction of even that minimal gap. What makes all of this sting a little more is the growing evidence that there may genuinely be something worth visiting in that system. In August of 2025, a team of astronomers using a major infrared-sensitive space telescope reported detecting a point source of light near Alpha Centauri, consistent with a gas giant, roughly the mass of Saturn, orbiting at around twice the Earth-Sun distance, placing it within the star's habitable zone. If confirmed, it would represent the nearest, coldest, oldest, and lowest mass planet ever directly imaged outside our own solar system. The story behind the detection is itself a lesson in scientific patience and caution. The initial observation came in August of 2024. To follow-up observations months later failed to recover the candidate's signal. It had apparently vanished. But detailed orbital simulations showed that in roughly half of all gravitationally plausible orbital configurations, the candidate planet would have simply been too close to its bright host star to distinguish from stellar glare during exactly those follow-up windows. Its disappearance wasn't necessarily evidence against its existence. It was consistent with a world on an elliptical orbit that had simply moved out of a detectable position relative to its star. Researchers also revisited an earlier, tantalizing 2019 observation from a separate ground-based observatory that had picked up a candidate point source at a slightly different position, near the same star. If both detections represent the same object seen at different points in its orbit, the combined data point toward a Saturn-mass planet with an orbital period somewhere between roughly a year and a half and 2.5 years, and a notably elongated orbit. This candidate remains unconfirmed. It could still turn out to be an instrument artifact, a stray clump of dust, or a statistical fluke. The scientists involved are explicit about describing it as a candidate rather than a confirmed discovery. The next real opportunity to test the finding comes when the telescope revisits the system at a point in the planet's orbit where it should, if real, become detectable again. If it reappears as predicted, the confirmation would be genuinely historic. If it doesn't, the candidate may simply join the long list of promising signals that eventually faded into statistical noise. But the sheer plausibility of this finding changes the emotional weight of the entire distance problem. Alpha Centauri isn't just an abstract nearest star system anymore. It may host a gas giant sitting comfortably inside the habitable zone of a sun-like star. And where gas giants orbit inside habitable zones, large moons, sometimes due to moons that could, in principle, host atmospheres, liquid water, and the raw chemical ingredients that, on at least one world we know of, eventually gave rise to life. This isn't speculation about some exotic system hundreds of light-years away. This is the star system next door, visible to the naked eye on a clear night from the right hemisphere. Its light reaching your retina after a journey of only about 4 years. Proxima Centauri itself already has confirmed planetary residence. Proxima Centauri b, discovered roughly a decade ago, is approximately Earth-sized and orbits within its star's habitable zone, the band of distances where liquid water could theoretically persist on a rocky surface. A second confirmed world, Proxima Centauri d, considerably smaller, at roughly a quarter of Earth's mass, was detected a few years later and confirmed more recently. A possible third planet, a candidate super-Earth, or mini-Neptune, on a much wider orbit, has been proposed but remains disputed, with more recent high-precision spectroscopic surveys unable to confirm its existence. But even the most promising of these worlds, Proxima b, carries a heavy burden of scientific uncertainty that no Earth-based telescope can fully resolve. Habitable zone is purely a temperature classification, the range of orbital distances where liquid water could theoretically exist on a rocky surface, given certain assumptions about atmosphere. It says nothing about whether a given planet actually has liquid water, an atmosphere at all, or any of the other conditions biology requires. And in Proxima b's specific case, there are real reasons for serious doubt. Proxima Centauri isn't a calm, steady star like our Sun. It's a magnetically hyperactive red dwarf, prone to violent stellar flares that can briefly multiply the star's brightness within minutes, bathing nearby space in intense bursts of ultraviolet and X-ray radiation. One especially powerful flare detected a few years ago was estimated at roughly 10 times more energetic than the strongest flares ever recorded from our own sun. These events aren't rare. They occur multiple times a year, sometimes multiple times a month. Any planet orbiting close enough to receive warmth sufficient for liquid water is also, by necessity, close enough to be repeatedly hammered by these outbursts. The implications for habitability are serious. Intense ultraviolet radiation can break down organic molecules on a planetary surface. Repeated X-ray bursts can gradually strip away atmospheric gases over geological time. Computer models simulating the long-term atmospheric evolution of Proxima b suggest it may have lost its atmosphere entirely within the first few 100 million years of its existence, potentially leaving behind a bare, irradiated rock with no meaningful protection against its hostile radiation environment. Some models allow for atmospheric survival under specific, somewhat optimistic conditions, a strong planetary magnetic field, or an unusually thick original atmosphere. But these remain speculative because we simply speculate of whether if praxively, because we simply say because it's original with sepness but it was equated with so much of what it's a rich of where to it it's pos it was with where it's equipped with what's it with its exopert before it with ek with sek would it wit of wit with get with paplepo to smack what big wick up with whip up with it ack up that with up There's also the question of tidal locking. Because Proxima b orbits so close to its star, completing a full orbit in roughly 11 days, gravitational interaction has almost certainly locked its rotation to match its orbit, meaning one hemisphere permanently faces the star in eternal daylight, while the opposite hemisphere faces eternally away into permanent darkness. The temperature contrast between the two sides could be extreme. Scorching heat on the day side, deep freezing cold on the night side, where the atmospheric circulation, if any atmosphere survives at all, could redistribute heat effectively enough to sustain habitable conditions somewhere on the surface remains genuinely uncertain, with different atmospheric models reaching different conclusions depending on their starting assumptions. The honest scientific summary, as of today, is this: Proxima Centauri b is an Earth-sized world sitting in the habitable zone of the nearest star, and it might be a sterile radiation-blasted rock, scorched on one side and frozen on the other, or it might host a thick atmosphere, active weather, and liquid water somewhere on its surface. We genuinely don't know. The data we can collect remotely, even with our most powerful telescopes, can't definitively distinguish between these possibilities. Settling the question almost certainly requires direct observation from within the system, a probe close enough to study the planet's atmosphere, surface, and magnetic environment up close. This is perhaps the cruelest dimension of the entire distance problem. The nearest potentially habitable planet might be habitable, or it might be sterile, and the only way to know for certain is to cross 40 trillion kilometers of empty space to find out. The question itself is perfectly answerable in principle. The distance simply makes it unanswerable from here. The nearest star system to our Sun appears to contain, at minimum, 2 confirmed planets around Proxima Centauri, plus a strong unconfirmed candidate around Alpha Centauri A, and possibly more. High-precision radial velocity surveys have placed increasingly tight constraints on undetected worlds throughout the system. ruling out large planets across many orbital configurations. But the sensitivity limits of current instruments still leave plenty of room for smaller, rocky worlds that simply haven't been detected yet. The Alpha Centauri system may turn out to be home to an entire family of planets, some rocky, some gaseous, some potentially habitable, all orbiting within the stellar system that sits practically on our cosmic doorstep. We can see these worlds. We can measure their approximate masses. We can constrain their orbits with growing precision. Within the coming decade, upcoming space telescopes may even be able to characterize some of their atmospheres directly, searching for chemical signatures like oxygen, methane, or water vapor that could hint at biological activity. This era of exoplanet atmospheric study isn't a distant fantasy anymore. It's actively beginning right now. And this is exactly where the distance problem stops being a mere technical inconvenience and starts feeling like something closer to genuine existential frustration. We can see the planets, we can study them remotely, in increasing detail. We can estimate their sizes, their orbits, their temperatures, and perhaps eventually their atmospheric chemistry. But we cannot visit them. We cannot send a probe that arrives within any human lifetime, using anything that currently exists. We cannot land an instrument on their surfaces. We cannot collect a single sample of their soil or atmosphere. We cannot confirm, with real certainty, whether any of these worlds harbor life, because a definitive detection of biology almost certainly requires being physically present in the system, with instruments sensitive enough to study surface chemistry or subsurface oceans up close. The universe has placed potentially habitable worlds at the nearest possible stellar address it could offer, and then surrounded that address with 40 trillion kilometers of impassable void. The invitation is fully visible. The door is firmly locked. This tension between visibility and accessibility isn't unique to Alpha Centauri, but it's most acute there because the stakes there are highest. Alpha Centauri is the proving ground. If we can't reach the nearest star system, we can't reach any star system at all. Every other potential destination in the galaxy is farther away, most of them vastly farther. The next nearest single star, a faint red dwarf, sits at roughly 6 light-years, nearly 50% farther than Proxima Centauri. Several other nearby red dwarfs lie somewhere between 7.5 and 8.5 light-years out. Sirius, the single brightest star in our night sky, and a system that has fascinated observers for thousands of years, sits at roughly 8.6 light-years. More than double the distance to Alpha Centauri, and these are still our genuinely closest stellar neighbors. The nearest confirmed Earth-sized planet, sitting in a habitable zone, beyond Proxima b itself, could easily be tens or even hundreds of light-years away. The Milky Way spans roughly 100,000 light-years from edge to edge. The overwhelming majority of its hundreds of billions of stars sit at distances that make Alpha Centauri's 4.24 light-years look like a rounding error by comparison. If the nearest star already demands either 74,000 years at current achievable speeds, or civilization-scale energy investment at the fastest speeds anyone has seriously studied, then the broader galaxy isn't a frontier waiting to be explored. It's something closer to a cosmic prison, where the bars happen to be made of distance, spaced at intervals of light-years rather than meters. The average distance between neighboring stars in our particular region of the Milky Way sits somewhere around 4 to 5 light-years. Alpha Centauri's distance isn't an anomaly we happened to get unlucky with. It's actually fairly typical for this part of the galaxy. There's no hidden closer star tucked behind a dust cloud somewhere. There's no secret stellar neighbor at half a light-year that surveys have simply overlooked. The local density of stars is what it is, and it places even our absolute nearest neighbor at a distance that dwarfs anything in ordinary human experience. Closer to the galactic core, stellar densities increase substantially in the densest regions. Neighboring stars can be separated by fractions of a light-year rather than several full light-years. In globular clusters, average stellar separation can shrink to roughly a tenth of a light-year. But even these dramatically reduced distances still represent trillions of kilometers. And the galactic core and globular clusters bring their own serious challenges along with their closer stellar spacing, intense ambient radiation, gravitational instability, and stellar environments hostile enough that habitability there becomes deeply questionable in its own right. Denser stellar neighborhoods aren't necessarily easier places to attempt interstellar travel. They're simply places where the gaps between islands are somewhat less vast. Consider what a mission to a star just 10 light-years away would actually require as a point of comparison. At Voyager-class speeds, the travel time exceeds 175,000 years. At 1% of light speed, roughly 1,000 years. At 10% of light speed, around 100 years. Energy requirements scale linearly with distance for a given velocity, so a mission to a star 10 light-years out demands roughly 2.5 times the energy of an equivalent Alpha Centauri mission. Communication delay doubles to over 20 years round trip. Every problem we've already examined, energy cost, transit time, communication isolation, material degradation, navigational precision, becomes proportionally worse. And 10 light-years is still, in galactic terms, our immediate backyard. The nearest star with characteristics closely resembling our own Sun, one that might plausibly host a planetary system broadly similar to ours, could easily sit 20 or 30 light-years away. A mission there at 10% of light speed would take 2 to 3 centuries. The communication round trip alone would span 40 to 60 years. The energy budget would run 5 to 7 times higher than an equivalent Alpha Centauri mission. We're already deep into multi-generational timescales and energy commitments that would dwarf anything any single nation has ever attempted, and we've barely left our local stellar neighborhood. Push further outward. The nearest major spiral arm of our galaxy lies roughly 6,000 light-years from our current position. The galactic center sits around 26,000 light-years away. The far edge of the Milky Way lies another 50,000 light-years or so beyond that. At 10% of light speed, the most optimistic sustained velocity any seriously studied propulsion concept has produced, a journey to the galactic center would take roughly 260,000 years. A full crossing of the galaxy would take on the order of 1,000,000 years. These aren't travel times in any meaningful sense anymore. They're evolutionary timescales. Entire species rise, change, and go extinct in less time than a single crossing of the galaxy at any speed humans have seriously contemplated. The galaxy, in this light, isn't a place you cross. It's a structure you inhabit locally, the way an organism might exist confined to a single organ system within a body that spans entire continents. We can observe the whole body from a distance. We can map its structure, measure its mass, study its dynamics in remarkable detail. But we live in one tiny neighborhood within it, and the distances separating us from any other neighborhood are extreme enough to impose something like a cosmic quarantine, not enforced by any authority or design, but enforced purely by the geometry of space itself. This is the deeper lesson Alpha Centauri teaches, and no amount of technological optimism can fully soften it. The universe seems structured in a way that makes observation remarkably easy and visitation almost impossibly hard. We can see stars scattered across the entire galaxy, using fairly modest telescopes. We can detect planets orbiting stars hundreds of light-years away. We can study the atmospheric chemistry of worlds in other solar systems using spectroscopy. We can listen for potential radio signals from civilizations thousands of light-years distant. Seeing, in a strange and almost generous way, is relatively easy. The universe is remarkably free with its photons. Reaching is an entirely different matter. Photons are massless. They travel at the speed of light, as a matter of default physical law. They cost essentially nothing to send and nothing to receive. Spacecraft are nothing like photons. They have mass. They require enormous energy investment to accelerate. They carry instruments that degrade and structures that age, and if crude, human beings who require food, water, breathable air, and some baseline of psychological stability across years or decades of confinement. The cost of physically sending an object across interstellar distances bears almost no resemblance to the cost of simply receiving light from that same distance. The asymmetry is staggering. We can photograph a planet orbiting Alpha Centauri using a space telescope that costs billions of dollars and sits a comparatively modest distance from Earth. We cannot visit that planet for any amount of money currently imaginable, using any technology currently in existence. There's a philosophical undertone worth touching on here, even if briefly. The universe, whether by indifferent natural process or some deeper structural necessity, seems to maximize the invisibility of its contents, while sharply limiting access to them. Stars broadcast their light freely in every direction across billions of years. Planets reveal themselves through subtle gravitational wobbles, periodic transits, and faint infrared glow. Distant galaxies remain visible across billions of light-years. Information flows freely across the cosmos at the speed of light. Matter does not. Matter stays trapped within its local gravitational neighborhood unless an enormous, almost civilization-scale quantity of energy is spent to move it elsewhere. The energy cost of moving matter between stars is so extreme that it effectively partitions the galaxy into countless isolated zones, each centered on a single star or star system, each separated from its neighbors by gaps that are perfectly transparent to light, yet functionally opaque to spacecraft. If you set out deliberately to design a universe that rewards curious astronomers, while quietly frustrating, ambitious interstellar civilizations, it would be hard to do meaningfully better than the one we actually live in. The sky is full of visible destinations. The space between them is full of nothing at all. You can look almost anywhere you want. You can go almost nowhere. Alpha Centauri crystallizes this truth more clearly than any other object in the night sky, precisely because it's the nearest star. It sits at the absolute extreme minimum of the entire distance function, the gentlest, most forgiving version of the interstellar distance problem that will ever exist. And it's already, by every relevant engineering metric available to us, firmly beyond our reach. None of this means interstellar travel is permanently, physically impossible. Nothing in known physics forbids it outright. The speed of light itself permits a crossing of 4.24 light-years in as little as 4.24 years for an object moving at that speed, and relativistic time dilation could meaningfully compress the subjective experience of the journey for travelers aboard a sufficiently fast spacecraft. There's no fundamental law of nature stating that a spacecraft can never reach Alpha Centauri. There's only the practical, present-day reality that doing so demands energy, engineering sophistication, and sustained institutional commitment on a scale no human civilization has ever demonstrated. Perhaps some future civilization will eventually demonstrate exactly that. Perhaps breakthroughs in controlled fusion power, antimatter production, advanced energy storage, laser propulsion, or some branch of physics not yet discovered, will shift the underlying calculus enough to make a real mission genuinely feasible. It would be arrogant to declare a problem permanently unsolvable, given how thoroughly the history of technology is littered with confident predictions of impossibility that were later proven wrong. But it would be equally arrogant to assume the problem will simply solve itself. Just because the answer is inconvenient, the distances separating stars aren't engineering challenges in the same category as building a bridge or launching a communications satellite. They're direct consequences of the fundamental geometry of our galaxy, the density of matter scattered through the galactic disk, the typical spacing produced by stellar formation processes, and the absolute speed limit imposed by relativity. These aren't dials that engineering can simply turn. They're boundary conditions within which all engineering has to operate. Alpha Centauri sits 4.24 light-years away. That particular distance wasn't chosen by nature for the convenience or inconvenience of human explorers. It's simply the distance at which the nearest star happened to form, roughly 4.5 billion years ago, within a region of the galaxy where stellar densities happen to be what they are. The distance carries no hidden message. It implies no intention, malicious or otherwise. It's entirely indifferent to human ambition, and that indifference may be the single most important thing this number ultimately teaches us. The universe doesn't rescale itself to match the capabilities of whoever happens to be looking up at it. It doesn't arrange its stars at conveniently reachable intervals for the benefit of curious civilizations that happen to evolve on one rocky world among trillions. The spacing between stars is a physical fact, not a design accommodation. Whether we find that fact thrilling or genuinely unsettling depends entirely on our own expectations, not on anything the universe itself is obligated to provide. What's certain is this: the distance to Alpha Centauri isn't merely a large number sitting in a textbook. It's a statement about the fundamental nature of the cosmos we happen to inhabit, a cosmos where light travels freely and almost instantly by cosmic standards, while matter remains stubbornly trapped, where information moves at nearly 300,000 kilometers per second, while our fastest spacecraft crawl along at 17, where the nearest star blazes brilliantly enough to see with the naked eye from half the planet, and yet remains far enough away to defeat every single machine humanity has ever built. And the genuinely unsettling part isn't the raw distance itself. 40 trillion kilometers is, in the end, just a number, something that can be written on a page, spoken aloud, converted cleanly from one unit into another. What makes the distance feel so heavy is the context surrounding it. This isn't the distance to some remote, obscure outpost on the far side of the galaxy. This is the distance to the nearest star, the absolute closest one, the starting line, the easiest possible case, the floor beneath which nothing simpler will ever exist. And everything beyond Alpha Centauri only gets farther from here. Every other interstellar destination, without a single exception, demands more energy, more time, more isolation, more risk, and a deeper, longer-lasting commitment than a journey to the one star system that happens to sit closer to us than any other in the entire universe. If the floor is already this high, the ceiling sits somewhere beyond the limits of sight altogether. That's what Alpha Centauri ultimately reveals, not just a distance, but a deeper truth about the architecture of the galaxy we call home. The stars are near enough to study in extraordinary detail. They remain far enough away to humble us completely, and the very nearest of them, shining quietly in the constellation Centaurus like a beacon meant for nobody in particular, is already so remote that successfully crossing the gap would stand as the single greatest physical achievement of any civilization in history that ever managed it. 4.24 light-years, 40 trillion kilometers, roughly 25 trillion miles, 268,000 times the distance from Earth to the Sun, 74,000 years at Voyager's current speed, over 400 years even at 1% of light speed, 21 years at 20% of light speed, using technology that doesn't yet exist, delivering a payload measured in grams, for a flyby lasting a matter of hours, with a return signal arriving more than 4 years after that. This is the nearest star. This is the easiest possible target in the entire observable universe, and it remains, even now, almost beyond comprehension.